All right, so my name is Keone Hon. I'm the co-founder of Monad. I'm here to talk today about a couple of major improvements that we've been working on in Monad that we think will help EVM execution be a lot more performant. So I'm going to talk about three major topics here. The first one is asynchronous execution. The second one is parallel execution. And the third one is addressing the biggest bottleneck for execution, which is actually state access through a custom database called MonadDB. Let's get into it. All right, so first of all, asynchronous execution. So just to give a bit of background, with most blockchains, there's interleaving between consensus and execution. So in most blockchains, consensus has execution as a prerequisite, meaning that we have nodes all around the world that are talking to each other. Actually, prior to talking to each other, the leader has to have executed the list of transactions. And then when the other nodes receive those transactions, they have to go execute them before responding. And so, for example, in Ethereum, we have a 12-second block time, but the actual time budget for execution, of course the budget is expressed in gas terms, not in time terms, but the gas limit is chosen to roughly be about 100 milliseconds of time. So 100 milliseconds divided by 12 seconds is about 1%, which is a crazy dilation factor from the amount of time that we have in the clock versus the amount of time that we actually have to execute. So just to illustrate this kind of visually, we have consensus, which is sort of the black boxes here, and we have the execution components, which are the small Perl components here. And you can see that in, just conceptually, consensus is taking up most of the block time, so it actually leaves a very small amount of time for execution. But if we do the following, which is to just have all the nodes first have consensus on the official ordering of transactions, and then once consensus completes on that official block, then move on to consensus seen on the next block while simultaneously executing the list of transactions you just consensused on. Doing those in two separate swim lanes, we can actually massively raise the budget for execution, which is kind of what you see here. So a couple of things to point out about this design. So the first one is that obviously the nodes are coming to agreement about the official ordering prior to executing, and then every node is actually going and executing independently. And so there's an invariant that we're utilizing here, which is that if all the nodes have the same state and then they all do the same list of work, then they should continue to have the same state. And then, there's some, you might be worried about whether there could be computational errors. We'll talk about that in a second. I guess the other thing to point out here is that nodes are coming to consensus, but when they're doing that, they actually have a delayed view of the state because the execution has not happened yet. So you might ask whether there are any wrinkles there. And then also just to point out, finality happens at consensus time. So, like I said, when the nodes, as soon as they've agreed upon the official ordering of the transactions, everything is deterministic from there. So that's consensus finality is actually state finality as well. Okay, so just a couple of finer details you might be worried about because the nodes are coming to consensus with a delayed view of the state. Could there be potential for spam, where someone can submit a transaction from an account that is now empty. And so we address that through something called the gas balance problem, which we could talk about more later if there's interest. And then lastly, you might worry about the nodes because they're all executing independently. What if one of them gets hit by cosmic rays and is now out of sync? And so we have a way of addressing that as well with the delayed Merkle group. Cool. So I'm going to move on though, just in the interest of time. We can find me later if you want to talk about it. So the second concept I want to talk about is parallel execution. So just to give a little bit of a problem statement about what's going on here. So I want everyone to think of execution as a black box whose job is just to get to the end state of a long list of transactions as if we just run those transactions one after the other. And the job of this execution system is to try to strategically do work more efficiently to get to that same end state. In Monad, we do optimistic parallel execution, which means that this black box is taking advantage of parallelism under the hood, but the behavior of the black box is still the same as if the transaction has just been run one after another. So I want to give a very simple example. So I want you to imagine that there's 3 transactions at the front of the block, and the first transaction, the starting state before this is that my account, my USDC account has 1,000 USDC inside of it, and Alice has 0 USDC, and Bob has 0 USDC. That's the state prior to this. And then there's 3 transactions. Let's say that the first one, might be a little hard to see here, but the first transaction is me sending Alice 10 USDC. And the second transaction is something like minting an NFT. And then the third transaction is me sending Bob 5 USDC. So in optimistic parallel execution, what happens is we just run all 3 of those transactions at exactly the same time, assuming they started from exactly the same state. So, transaction 1 will have, the thing I forgot to say. So with optimistic parallel execution, we run all these transactions in parallel as if they started from the same state, and we just record all of the inputs that were read in and all of the outputs, like the pieces of state that have been mutated. So when we run transaction 1, we start with an input of my USDC account has 1,000, and the output is that my USDC account has 990 because I set 10 to Alice. And of course, Alice's input is like 0, and then output is 10. Just ignore the second transaction. And then the third transaction, because we're running it in parallel, it doesn't know about the first one, so it would also have an input of my USDC account is 1,000, and then the output is my USDC account is 995. So with optimistic parallel execution, the way that things work is we first run them in parallel, and then we step through those pending results that we produced, and we try to commit them serially. So first we would commit the first pending result without any issue. Then we commit the second pending result, which was unrelated, so no issues. And then lastly, we would try to commit the third result, and that third result will actually fail because now when it was run, it had an input of 1,000, but now we know that the input is no longer 1,000, so we just reschedule work. So I'll say this again, but just in a kind of better, more succinct way. So optimistic parallel execution is basically the practice of doing 2 stages of work. The first stage is executing many transactions in parallel, thus surfacing all of the state dependencies for all of those transactions and pulling in all those values from SSD, pulling them into cache. And it also, in this first pass, it also has the result of producing all these pending results that keep track of the inputs for those transactions and the outputs. Then in the second phase of execution, we're committing all those pending results one by one, or rather trying to commit them. And if there's ever a pending result whose inputs have since mutated, then we just go and re-execute. And the thing to keep in mind is that with this re-execution, it's actually quite cheap because almost all the time, all of the inputs for that re-execution are already in cache. And it's important to know that the biggest bottleneck for actual execution is not the CPU time of doing this computation, like doing adds or multiplies or jumps or even SHA-3s. Like all of these opcodes are really cheap. What's expensive is pulling the state dependencies from cache. So because of that first pass where we pulled all these dependencies into cache, we're actually in that second pass able to execute very efficiently, either immediately committing or if we need to re-execute them, re-executing quickly. Cool. So lastly, I want to talk about the third major improvement within Monad, which is addressing the state bottleneck, making state access much more efficient. So I want to point out a couple of quick things. The first thing is that efficient parallel execution itself depends on efficient state access because the biggest bottleneck for execution is reading stuff from SSD. So just to give you some kind of numbers on SSDs, they're actually really awesome nowadays. There's been a lot of progress. So a high quality 2 terabyte NVMe SSD supporting 1 million IOPS, so 1 million IO operations per second, costs about $200. So SSDs are very high bandwidth, like imagine a bottle with a really big bottleneck, but they're slow compared to reading data from memory. So the cost of one read is 40 to 100 microseconds as opposed to a fraction of a microsecond for reading from memory. So it's really important if we want to get really fast execution to actually saturate that bottleneck of those SSDs. So going back, we really need to be able to pull these dependencies from SSD super efficiently. And the other thing you need to know about the state access problem is that Ethereum state lives in a Merkle tree. And I think, most people in the crypto space kind of, have seen the diagram of the Merkle tree that has the Merkle root up at the top. They know to look up a value, you have to navigate all the way down to one of the leaves. But the thing to know is that for a lot of blockchains, including Go Ethereum and others, or blockchain clients like Go Ethereum and others, this Merkle tree is actually stored inside of another data structure because the backend for Go Ethereum, for example, is LevelDB, which uses the LSM tree as a data structure. So the thing I want to emphasize is that when you want to look up one value from the Merkle tree using Go Ethereum's data structure, you have to traverse all the way down to the bottom of this Merkle tree. But each one of those traversals, like each node that you visit, is actually going and traversing through another tree under the hood in order to just get that value for that one node. So it's almost like quadratic in terms of the number of lookups you're doing to the underlying tree. So basically storing the Merkle tree natively on disk is a significant improvement because then instead of doing this quadratic lookup, we just can look things up directly. There's some other improvements on MonadDB, such as support for asynchronous I/O. Also, we bypass the file system. But just in general, this is a really efficient way to deliver performant parallel execution. All right, I think that's it. So just to summarize, 3 major things: asynchronous execution, number 1. Number 2, parallel execution. And number 3, MonadDB, efficient state access. Thank you. Are there any questions? Yes, in the back.
When will we see it in an execution client?
When will we see it in an Ethereum execution client?
Yeah.
I think that depends on the Ethereum roadmap as well, but within the Monad team, we're extremely passionate about going really deep down the path of improving execution and then contributing back to the Ethereum space. So we will propose some of these improvements as EIPs and then work with client teams to try to get some of these integrated. Thanks. Yes?
Okay, this all sounds like really cool. What are the drawbacks, or what might be things that we might lose with this?
Well, I think it depends on the specific improvement. So with asynchronous execution, it's like definitely a paradigm shift in the sense that now nodes are not doing strict state machine replication. They're just agreeing on the official ordering, and then they have kind of like a check on a lagged Merkle root. But if you wanted to be very, very confident about the state of the world, you'd run a node yourself. So we put a lot of effort into making it really cheap for users to run a node themselves. But just in general, like you shouldn't do that if you want to actually know the state of anything. Because if you just query Infura for a value, they might lie to you. So yeah, running a node yourself is quite important. All right, I think that's it for questions. Thank you so much, guys.